Here's something funny. Okay, welcome to the Tutte Colloquia. We're very happy to have Rob Morris here today. So Rob is is a professor of mathematics from IMPA from Brazil. He specializes in probabilistic and extremal combinatorics. Many of you probably know his work that Rob is Ferguson Prize winner of 2018, and he's well known for his influential work on the hypergraph containers method. He's going to talk about flat Littlewood polynomials exist today. So Rob, stage is yours.
Thanks very much, James. So thanks very much for the invitation. It's a great pleasure to be speaking at the Tutte Colloquium. This is my first time in Waterloo, so I'm enjoying it very much so far. Hopefully, I'll be able to come in real life at some point in the future. So I'm going to tell you about Littlewood polynomials. I'm not going to assume that you know anything about them at all, and so the main sort of things I'm going to be assuming are some basic familiarity with combinatorial and probabilistic things. So in particular, the proofs will be all completely combinatorial. So it's joint work with Paul Ballister, who's now in Oxford, Bela Bolabash, I guess you all know, of Memphis and Cambridge, and two young people. So Julian Hazrabude is a brilliant young mathematician in Cambridge, who was my postdoc in IMPA for a little while. And Marius Tiber is a recent student of Bela's, who will be a postdoc in IMPA next year, and then after that is going to Oxford. This work was all done in Lucca, Italy. We spent a very enjoyable month there working on this problem. Okay, so what is a Littlewood polynomial? It's just a polynomial whose coefficients are either -1 or 1. Okay, it's a polynomial of degree n with the coefficients are all just plus minus 1. Okay, so a very simple and nice combinatorial object. And our story begins in 1957. So as many stories begin with a question of Erdős, who asked, and he didn't work on these polynomials too much, but he asked this very perceptive question. So does there exist a Littlewood polynomial of degree n that is always roughly root n distance from the origin? So it never gets too far away from the origin and also never gets too close. So that's for all z complex numbers of order 1. So if you sort of look at the trace of this polynomial as you go around the circle, does it always stay basically near a circle, except scaled up by root n? Root n is the right thing just by Parseval. So the sum of the squares of the epsilons n, and therefore it's sort of on average distance root n away. And this question inspired Littlewood, who'd been thinking about Littlewood polynomials for a while by this point, and this inspired him to think about these kind of questions. He spent a large part of the next 10 years thinking about questions related to this question of Erdős. And he made lots of very beautiful and influential conjectures about them. And in particular, he conjectured that the answer to this question of Erdős is yes. In his 1968 collection of 30 problems and analysis, he spends quite a bit of time talking about this problem, about various failed approaches. Okay, so this may look like a slightly strange question. So let's start out by looking at some pictures, just to get a hang of it. So the first thing you might try is, okay, what happens for a random polynomial? And so I'm afraid I can't program or draw pictures, but there's a beautiful survey on this problem by Odlyzko from just a few years ago, and he has lots of lovely pictures, lots of lovely simulations that he did. So I have borrowed some pictures from him. So this is a sort of quasi-random polynomial, and as you can see, it goes round and round and round, and it spends quite a lot of time near 0, and it goes occasionally quite far out. And you might guess from this that sort of the density of this image of the polynomial looks a bit like a Gaussian, right? So it spends most of its time near the center and then it sort of has some chance of being fairly far out, and that's more or less true. So the maximum of a random polynomial is roughly root n log n. So up to a log factor, the upper bound is true even for a random polynomial. Okay, but the lower bound is terrible, right? This thing gets super close to the origin. So we would like a hole in the middle as well, and for a random polynomial, we don't get it at all. Okay, at least the upper bound's not too far away. So the first question you would think is, okay, well, can we get rid of this log in the upper bound? Can we at least prove there exists a polynomial that satisfies the upper bound, constant root n? And that was proved actually a long time ago, before the question was even asked. Harold Shapiro, in his master's thesis, gave a construction, which was then rediscovered by Rudin a few years later, that there exist little polynomials of degree n where the upper bound holds. So they're always at most 5 root n. So the image of the circle is always at most 5 root n. And the construction is extremely simple. So here it is. So it's a sort of inductive construction. So you have these two polynomials, pt and qt, which are degree 2 to the t. And you make pt plus 1 by taking just taking pt and qt and sticking them next to each other. And you make qt plus 1 by doing the same thing, except one of them is flipped. One of them is reversed. Okay, so they have this sort of fractal structure. So it's not hard to see that these are Littlewood polynomials of degree 2 to the t minus 1. And it's also not difficult at all to prove this upper bound of 5 root n. This is just a simple, a very short, simple argument. By the way, I would be extremely happy if you ask questions. So please don't be shy. If anything is unclear, please jump in and ask me. Okay, so there we have some construction for the upper bound. And here's a picture of these polynomials, again taken from a Lidzko's survey. So as you can see, they're sort of tucked in very nicely on the outside, but they don't do very well at all on the inside. So this is not a good candidate for the lower bound. I mean, in fact, they look sort of like a random polynomial from the perspective of just what's happening in the sort of the middle of this picture. And that will actually be useful to us later. So we're going to use these polynomials again later. Okay. Okay, so that's great. So where does sort of the probabilistic combinatorics come in? Well, it starts with some famous work of Beck, who in the early 80s discovered introduced a new probabilistic technique in discrepancy theory, sort of based on the pigeonhole principle, but applied in a very clever way, so using probabilistic ideas. And so he discussed this with Spencer, and Joel was inspired to use this method to prove the following famous theorem, known as the 6 standard deviations to suffice theorem. So probably most of you know this, but I'll say it anyway. So for any set of n subsets of 1 up to n, there exists a red-blue coloring of the vertices such that each of the sets has small discrepancies. So discrepancy being the difference between the number of red vertices and blue vertices. So every edge is basically balanced up to an error of constant root n. Okay, and that's the best you can hope for. This was a conjecture of Erdish, I believe. It doesn't really look like this has all that much to do with our problem, but in the same paper, Spencer used the same technique to show that, to give a non-constructive proof, so a probabilistic proof of the Shapiro-Rudin theorem. So he showed there's not just one Littlewood polynomial degree n, but there's actually exponentially many, with that are always at most constant root n on the unit circle. Okay, and the exponent gets better as the constant gets bigger, as you might expect. Okay, so so you can find these things probabilistically, which is sort of encouraging for someone of my inclination. And this is, I think, so Julian suggested this problem, and I think this is also what grabbed his attention. Okay, so upper bounds look like they're pretty good. How about lower bounds? So none of the examples we've seen so far are at all good for lower bounds. Okay, so let's look at some examples, perhaps, just to see if there's any chance. So here's a nice example. So the Barker polynomial is a degree 12, and is an extremely good example. Unfortunately, so these Barker polynomials, they don't exist for a degree larger than 12. So I won't tell you the definition, but there's some family polynomials. Adlitsko did an exhaustive search of polynomials up to degree 50, and he found this example for degree 50. This was like a pretty good example. So it's got a nice hole in the middle, and it doesn't go out too far either. Okay, there's some annulus which looks like it's a sort of maybe a constant factor. A bit more evidence. So for degree 92, he found this example, which is the best skew symmetric one, which looks like it's doing about as well as the best one of degree 50, right? There's perhaps some evidence that these things are not getting better or worse as the degree gets larger. Okay. So all right, that's some numerical evidence. How about heuristic? So how should we think about this problem? Well, let's think about 2 points on the circle and their images under this polynomial. Well, by this idea that, well, it should be sort of roughly Gaussian. If we pick the polynomial randomly, then it should be sort of the position of the polynomial should be roughly Gaussian. Then each of them should be within this circle of radius delta root n with probability about delta squared. Yeah, that's the area of this this circle about the origin. Okay, but they're not independent. They're highly correlated if the points are close on the circle. And it turns out the correct scale is roughly 1 over root n. So if the points are within some small constant over n, then you expect their images to be highly correlated. On the other hand, if they're sort of much further than 1 over root n apart, then you expect them to be sort of essentially independent. Okay, so this is for a random polynomial, but okay, just to get us ourselves in the right mindset. Okay, so we have to somehow deal with these dependencies. Okay, so what does this suggest for a heuristic calculation? Okay, let's think about the roots of unity. So the mth roots of unity for some m. If we take m being order n, then the ones that are close together are sort of, so adjacent ones are just at the point where they're becoming independent. Well, what's the probability that all of these points, that none of the images of the roots of unity fall in the circle? Well, each one is in it with probability delta squared. So probably they all fail. You might hope with this kind of, they're almost independent except for, the ones very close together. You might hope to prove this probability is roughly 1 minus delta squared to the m. And if delta is small, this is much bigger than 2 to the minus n, right? Because m is of order n. Okay, so if delta is a very small constant, and m is a constant times n, and if this sort of intuition is roughly correct, then the expected number of flat Littlewood polynomials should be large, right? Should actually be exponentially large. Okay. Are there any questions about this this heuristic? I'd sort of quite like you to, perhaps even more than the proof, then I would like everyone to be sort of happy with this heuristic. Okay, so if there are questions later, I can always go back. So just please let me know. Okay, so right, so using this kind of this very simple heuristic, one would hope that one could find these things randomly, right? There's enough of them that you have some chance of maybe doing some kind of random process. Okay. So what was known before our work? Well, there's a simple recursive construction that was found a long time ago that gives n to some power, so n to the power 0.4 or so, by Carol, Eustace, and Figuel. That was the best bound that was known before our work. If you allow a sort of richer family of polynomials, then you can do actually a lot better. So Kahan proved in a well-known result from 1980 that if you allow your coefficients not to be plus minus 1, but any point on the circle, you can actually do much better. So you can find the so-called ultra-flat Littlewood polynomials, where they always stay very close to the root n radius circle. And using this construction, Beck managed to show by a very clever argument that actually you can restrict your coefficients to be roots of unity, as long as sort of your number of roots of unity is at least 400 or something. Then you can prove there are flat polynomials with those coefficients, and as your k gets bigger, then your ck approaches 0. This generalizes Kahan's result, but using it. So I would note that these results all sort of fit in with our heuristic that we had. So if you allow kth roots of unity for your coefficients, instead of having 2 to the n choices, you have k to the n choices. So that should allow, by our previous heuristic, it should allow your delta to be bigger. And as k tends to infinity, then your delta should be able to approach 1, right? So the heuristic calculation that we had a minute ago, this is all sort of fitting in with the story of these results. So it maybe makes us feel a bit more confident that it's really describing what's going on. Okay, so if 2 to the minus n is replaced by k to the minus n, and m is still of the same order, then we can allow delta to get sort of closer and closer to 1, right? And still have this be true. Okay, so that's what was known. And this is what we proved. So we proved there exist flat Littlewood polynomials. And note that the lower bound, the constant in the lower bound is quite a lot worse than the constant in the upper bound, sort of reflecting the fact that the hard part of the theorem is proving the lower bound. So the difficult thing is to find polynomials that avoid the origin. The upper bound doesn't quite come for free, but it's certainly much easier. Okay. So let me start by giving you a very rough sketch of the proof. Then I'll give a sort of more extended sketch, and then I'll give us a tiny bit of sort of technical detail, just a couple of slides of technical detail. Okay. So here's the very rough sketch. So up to polylog factors. So let's imagine that we don't want to prove this. We just want to prove with up to some polylog factor. Okay, so the first idea, perhaps the key idea even, is to use the 2 dimensions of the complex plane independently. Okay, so in one of the dimensions, let's say the x-axis, we're just going to choose something random. So we're going to have a real cosine polynomial, an imaginary sine polynomial, you'll see on the next slide. And we're going to choose the real part to be basically random. And so most of the time, that's going to be okay. But it's going to pass through 0 a bunch of times. And whenever it passes through 0, we need to push it hard in the vertical direction. So in the other dimension, instead of the vertical axis, we're going to try and push the polynomial away from 0 whenever it's small in the first dimension. And we're going to do that using ideas from discrepancy theory. So ideas that originate with this work of Beck in the early 80s. Okay, so that's our basic plan of attack. So I should say that the proof of this theorem is it's really surprisingly simple. So I don't want you to come out of this thinking that this is a complicated proof at all. I want to try and impress on you how simple and nice this proof is. Okay. Okay, so what's this first step? We need to use the two dimensions independently. So let's first break up a polynomial into a real polynomial and an imaginary polynomial. Okay, and that's not too difficult. So we're going to partition 2n into two sets C and S. And we're going to only consider polynomials where, so epsilon k is equal to epsilon minus k in C, and it's equal to, it's the same sign if you're in C, and they have the opposite sign if you're in S. So this may look weird because there's no minuses yet. So what am I talking about? Well, we're actually going to look at a polynomial that goes from, so what should I say? It's a power series on the polynomial or whatever. But goes from minus 2n to the powers are going to go from minus 2n to 2n. But why are we allowed to do that? Well, if we just multiply by some power of z, we're not changing what's going on because z is of modulus 1, right? So we're just rotating it. So it doesn't change the problem to multiply the polynomial by some power of z. Okay, so we can multiply it by z to the minus 2n, and we're in the same situation. Okay, and now we have this thing that's symmetric about 0. And now what I said just before perhaps makes more sense. And you'll see that if you're in C, the epsilon of k and epsilon of minus k are the same, so you get a cos. If you're in S, then the signs are opposite, so you get a sine. So just using the usual whatever expression of cos and sine is exponentials. Okay, and z is e to the I theta, right? So you're on the circle, so we can write z as e to the I theta. So this is just sort of basically totally standard thing to do. And so now we have this nice real cosine polynomial, an imaginary sine polynomial. These things may look a little bit scary, but don't worry, they're really not too scary. Okay. Okay. So our aim is to choose these sine and cosine polynomials, so these epsilon k's, such that neither of them ever gets very big. So this is in the x-axis, you don't get very big, in the y-axis, you don't get very big. So that's good. And whenever the cosine polynomial is small, the sine polynomial is large. Okay, so the cosine polynomial you should think is being random. So it just kind of wanders around randomly on the x-axis. And whenever it gets close to 0, we push it super hard vertically, either up or down. Okay, so we're going to make sure the sine polynomial is big wherever the cosine polynomial is small. Okay. Okay. Right. So, how are we going to do that? Okay, so that we want this polynomial to be large. Well, okay, let's suppose we've already constructed the cosine polynomial, and let's look at the places where it's small. So it's flying back and forth along the x-axis, and there are various intervals on the circle where the image is small. Let's suppose there's m of them. Okay, just let m be the number of intervals. Okay. So we want to choose the coefficients in S so that on each of these intervals, the sine polynomial is large. Right? Okay, so what does each choice do? So how are we choosing? When you choose an epsilon k, you're pushing each of these intervals vertically by sine k theta. Okay. Well, what's sine k theta? It's just some number between -1 and 1. And if the thetas are fairly far apart, then those numbers look basically independent. Right? So maybe we can think of these sine k thetas as being random elements of -1, 1. Okay. I mean, really, I should say interval -1, 1, but let's just say set -1, 1 to make it even simpler. Okay. It's just the heuristic again. Okay. And what do we need in order to do that? I'm sorry, I think I have to go and open my door, unfortunately. Give me a second. I'll let you do 2 minutes to think about this while I do that. Sorry, back. Right, so if these intervals, these m intervals, if they're short, then basically this sine k theta should be constant on them. And if they're far apart, they should be basically independent. Okay, so if we chose the cosine polynomial randomly, then we've got some pretty decent chance these intervals are short and far apart. So we have some chance of this working. Okay. Okay. Right. So now, in case things are getting a bit technical, let's have a toy problem that explains what we're going to try to do. Okay. So even if you haven't understood the last couple of slides, you can hopefully understand this. So we're going to try pushing this polynomial, and here's the toy problem that explains what's going on. So suppose you've got the line, so the integers, and suppose you have m balls, and let's say they all start at 0. Okay, and these m balls correspond to these m dangerous intervals. Okay, we have to push them all far away from 0. Okay, vertically. And what happens? Well, for each k, we have to choose an epsilon k, plus minus 1. And for each k, about half of them are going to be positive, and about half of them are going to be negative. And which half it is going to be basically random. Okay, it's going to look like it's random. Okay, so these are the sine k thetas. The value of sine k theta on each interval looks a bit like just a random plus minus 1. Okay, so let's think of the black balls as being the plus ones and the white ones as being the minus ones. And we get to choose epsilon k, and what that does is it pushes the black balls right and the white balls left, or vice versa. Okay, so we get to choose if we push the black balls left and the white balls right, or the black balls right and the white balls left. And that's it. And then that's for a single k. And then for the next k, we get a new independent set of, the balls right. The half move left, half move right. And then for the next k, we get a new independent subset. It's not quite true, but it's sort of roughly true. And we get to decide if we push them left or right. And we repeat n times. Okay. So, okay, you see? So I pushed the black balls left, then we got a new random set, black balls went right, new random set, black balls went right, new random set, black balls went left, new random set, black balls went left. Okay? And what we're trying to do is we're going to clear out a space in the middle, right? So that all the balls are far away from the middle. So how can we do that? So we spent, a couple of weeks or so coming up with kind of crazy, complicated strategies to try and do this. I think even the toy problem seemed quite interesting. So after I gave a talk on this a few months ago, and I had a sort of exchange some emails with Joel Spencer and Nikhil Bansal afterwards, and they were quite interested in this toy problem. It seems like it's really quite non-trivial to solve this properly. But luckily for us, we don't really need to solve this properly. We just need something sort of relatively weak, as it turns out. So we were trying for a while to really try and solve this toy problem properly. But then what we realized eventually was you can do something quite simple. So here's a strategy, a very simple strategy for pushing balls that's good enough for us. So for each ball, we're just going to choose a direction at the beginning without having seen anything. Okay, I'm lying slightly, but if you don't care about logs, choose direction left or right. And then at each step, that ball is just going to vote to move in that direction. Okay. And we just choose the direction with the most votes. Okay, so at each step, each ball votes to go in their preferred direction, and we just choose, we just do what the majority says. Okay. So how far should we have pushed each ball after n steps? Well, the influence of a ball in this voting system is about 1 over root m, right? That's the chance of its vote being pivotal. So about 1 over root m proportion of the time, a ball will get to go his own way, and the rest of the time randomly. Right? So the drift is about 1 over root m. So after n steps, you expect to have moved about n over root m in your preferred direction, with some error of about plus minus root n. Okay, this is sort of the typical behavior of a ball. So it will drift because its influence on the voting scheme is 1 over root m. It will drift at about that speed in its preferred direction. Okay. Okay. So, well, so we might hope that after sort of about m steps, the main term gets bigger than the error term. So we need at least sort of order m steps to have a chance. Then we might hope that after sort of large constant times m steps, then we're really kind of are getting somewhere. And so I don't actually know the correct answer to this question. In particular, so there's 2 versions of this process, an online version and an offline version. And I think that what I just said is basically correct for the offline version, when you get to choose, you get to see all of the random sets at the beginning. But for the online version, it may well be false. It may be you need an extra log. Anyway, so there's a nice problem that if anyone wants to chat about afterwards, then I'm very happy to chat about it. Anyway, what this says is you're going to need about m steps, right? And remember, m is the number of bad intervals. And we were kind of expecting that to be, well, if you take a polynomial of degree n, it will be near the origin about n times. So this is not looking very good for us. It looks like basically we've lost by a constant factor. And the solution to this problem is also incredibly simple. So this proof is a series of steps, each one of which is incredibly simple. And sort of you kick yourself in hindsight that you didn't think of it in 30 seconds. And perhaps some of you have already thought of the next of what this next step is. Please shout out if you have an idea. So it's okay. So this is the end of the gentle heuristic. I'm now going to do something a little bit more technical, just for maybe 3 slides. Okay. And then that'll be all the technical part. Okay. So what are we going to do? So the next very simple idea is we choose our cosine polynomial not to be degree about n, but to be degree gamma n for some very small constant gamma. So remember, our cosine polynomial is this real one that's random. So it's whizzing around randomly, and we're worried about when it's these intervals. We have m intervals where it's close to 0. Now, if this cosine polynomial is degree only gamma n, then there are only 4 gamma n intervals when it's small, right? Because every time it goes into this dangerous bit or out of it, that's the root of some polynomial, right? And so there are sort of 2 gamma n roots for this one and 2 gamma n roots for this one. It's a cosine polynomial, so you get twice as many roots as you expect. Twice as many roots of the degree, not just the degree. Okay? So just whatever it's called, the fundamental theorem of algebra or whatever, tells you that if you take C to be small, so you take your degree of your cosine polynomial to be small, you have at most 4 gamma m dangerous intervals. And now suddenly we're in great shape because now our m is much smaller than n. And therefore n over root m is much bigger than root n. And so our drift is much bigger than our typical variation. Right? So as n over root m is much bigger than root n. So this first term, sorry, I wish I could point at things, is much bigger than the error root n if m is little o n. Right? Okay. So now suddenly we're in much better shape. Okay. Aha. And okay, so now we want to construct a cosine polynomial, and the way we actually do it is using the Rudin-Shapiro polynomials, because we also want this upper bound. So a random polynomial would almost do the job, but the Rudin-Shapiro polynomials are just better. Okay. And there's a slight trick here that what we do is not quite take the original Rudin-Shapiro polynomials. We take this this sort of this z to the capital T factor, which is just something that sort of whizzes them round very fast. So you'll take them and you modify them just by making them go much faster in this funny way. And what that does is it makes it easy to prove that the intervals on which this polynomial is small are short and well separated. So what it basically says is you can't go into this interval and then just hang around there for ages before you come out again. This z to the capital T term, once you're in it, it forces you out pretty quickly. But it also prevents you from coming back too quickly. Okay, so so I don't expect that to be obvious, but it isn't very difficult to prove. It's it's 2 or 3 pages of very sort of elementary calculations. Okay. Okay. Right, and now what do we have? We have few bad intervals, only gamma times n. And those intervals are short and well separated. And those were the 3 things we wanted to make our heuristic work. So now we're in a position where, I mean, we don't see what's going to go wrong anymore, right? We have our cosine polynomial, and suddenly our heuristic looks like it should work. So all we have to do is make it work. Okay. Okay. So how do we do that? Well, if we didn't mind losing polylog factors, then we're almost done at this point, because we could just choose gamma to be sort of some polylog, something going to 0, like say log n squared, and then essentially everything would just work. But okay, now we've come this far. Let's really get the result we want. And the way we get rid of these polylog factors, just like Spencer got rid of the log factor in the upper bound, is to use Becks theory, basically, to use these ideas from discrepancy theory. And the version, so I have more heuristic first. So, right, sorry, this is a heuristic for why we should be done if gamma is very small. So the polynomial should be pushed on each interval to sort of distance, it's n over root m plus or minus. Well, okay, so root m was optimistic, but in the worst case, it should be root n log n. And if gamma is 1 over log n squared, then our drift beats even our worst case. So we can just take some union bound of all of the bad intervals and we'd still basically be happy. Okay? Right. But to remove the logs, we need to do something a bit cleverer. And the exact statement we use is this lovely result of Loveit and Mecca, which is it's a slight generalization of Spencer's theorem. And there are 2 really nice things about this result. So it maybe looks a bit scary. There's 2 really nice things. So one really nice thing is that it allows you to take these constants, these c's, as many of them as you like, as long as they're decaying in this way, this condition, the sum of e to the minus ck squared should be not too big. Okay, so you should think of these things as being constants at first, but then once you get beyond n, then they need to start growing, basically, so to make this this sum converge. Okay. And what they give you, so what they give you is if you're in this sort of n-dimensional cube, they allow you to find a a point on the boundary such that you don't go more than distance root n in any of the special directions vk. Okay, so we have these m special directions that we're worried about, and you make sure that your x minus x0, so your starting point to your final point on the boundary, didn't go too far in any of these directions. Okay, so this is a tiny bit technical, but the other really nice thing about this theorem is their proof. And what their proof says is, all right, how are you going to prove this? Let's just start a Brownian motion at x0. And let's run it. So there's a bunch of conditions we want at the end. Each of those conditions corresponds to a hyperplane. So you have these m different hyperplanes all cutting through your cube. And what you do is you just kind of run this Brownian motion until it hits these things. And when you hit a hyperplane, you just continue the Brownian motion inside the hyperplane. And then you hit another one, and then you continue in the sort of that Brownian motion in the intersection of these two hyperplanes. When you hit one of the sides of the cube, then you carry it in the side of the cube. And you just run this Brownian motion until you've fixed a constant proportion of your conditions, of your coordinates, and then you stop and you start again, and you sort of see what you have left, and then you just iterate this process. It's a really beautiful and simple argument, and so I highly recommend this paper to those who don't know it. Anyway, for us, it's super useful because what do we need to do? Well, this allows us to do the two things we need to do. The two things we need to do are, we need to choose which direction we're going to push each ball in, right? Are we going to push for each dangerous interval? Are we going to push it up or are we going to push it down? And so the first thing we can do is we just look on each interval of the average of sine k theta. That gives us a bunch of vectors. If you just apply this theorem to that set of vectors, it tells you which direction to push in. And then, once you know which direction to push in, the theorem then tells you what epsilon should be. So it tells you what all of the epsilon k should be by applying it to this more complicated vector. So what is going on here? So we're not only controlling the the direction it's telling us. So basically the directions tell us, okay, now you know that in each direction you should be able to push this far. And now we want to say, okay, you actually can find some epsilons that really do push it that far. Okay, so what are we saying? What we said was we're pushing in each direction by some large constant times root n. And what this discrepancy theory thing says is actually you get that plus or minus root n. Right? So this heuristic tells you should push to distance 1,000,000 root n, and this says you really do push to 1,000,000 root n plus or minus 1,000 root n. Okay? And this more complicated thing is saying, but that just tells what happens on certain points in these intervals. But if we also control the gradient and the second derivative and the third derivative and all the derivatives, then by Taylor's theorem, we're okay in the whole interval. Okay? So perhaps that last thing is a little bit technical, but basically what this is saying is the picture in your mind should be, we have these m bad intervals, we've chosen directions so that we can, based on their positions and these signs, so that we think, okay, we should be able to push each one to like 1,000,000 root n. And then discrepancy theory tells us that we can actually choose some epsilons so that we push the distance 1,000,000 root n plus or minus 1,000 root n. Okay, and so everybody ends up super far away from zero. Okay, so I apologize. That's the end of the technical part. So let's just remind ourselves what the theorem said again and the very gentle sketch. So the theorem is there exist flat Littlewood polynomials. And the proof is as follows. We choose a cosine polynomial that's at most root n everywhere and at most delta root n on few, short, well-separated intervals. And the way we did that was picking the Rudin-Shapiro polynomials, sort of randomizing them a bit, and making sure they have low degree. In each interval, we choose a direction to push vertically, and we use results from discrepancy theory to make sure that we can push it by the expected amount plus or minus some small error. The error is root of order root n. Okay. And what that gives us is a sine polynomial, an imaginary sine polynomial that's at most 1,000 root n everywhere and at least 10 root n on the dangerous intervals. Okay, we only care about what happens on these m dangerous intervals when the cosine polynomial is small. Okay. Okay. So I think I have 3 minutes left, if that's right. If I got my timing correct. So that gives me time to tell you 2 open problems. So the first open problem is it's also a question of Erdős from the same paper. So do there exist ultra-flat Littlewood polynomials? So can you make the 2 constants the same? So Erdős thought that maybe he thought that this might even be true for the coefficients with modulus 1. But as we saw earlier, Kahan showed that that's false. So there do exist ultra-flat polynomials with complex coefficients. But numerical evidence that I showed you earlier of Adlitsko suggests that the answer should actually be no for Littlewood polynomials. And perhaps even more convincingly, our heuristic also suggests the answer should be no. Right? Our heuristic we had earlier suggested this probability should be like 1 minus delta squared to the n. And so when delta gets close to 1, so this should be sort of super exponentially unlikely. And because we only have 2 to the n Littlewood polynomials, there's no reason to expect these things to exist. Okay. So my strong suspicion is that these things do not exist. So both the heuristic and the numerical evidence point in that direction. But I have no idea how to prove it. The final open problem is a sort of is another very well-known conjecture, but it's nice to advertise it to people who don't know. So Komlos conjectured in the 1980s, or perhaps even earlier, that if you take n vectors in any number of dimensions, might as well be n, unit vectors, then you can find some sum and difference of them. So some sum of epsilon k vk with epsilons being plus minus 1, such that the infinity norm is constant. Okay. This seems sort of just far too natural and beautiful to be unknown. But the best we know is Spencer proved order log n, using again in the same paper, using similar ideas. Banashik, I hope I'm pronouncing that correctly, used a geometric method to improve this to root log n, and Bansal, Dadish, and Garg gave another proof of this using semi-definite programming, so sort of more probabilistic proof. This are really, so I don't know the Banashik proof, but this this proof of Bansal, Dadish, and Garg is really lovely. Oh, and just to note that this conjecture would also imply the famous Beck-Fiala conjecture in discrepancy theory. Okay, so thanks. I'll stop there. Let me put the theorem back.
Thank you very much for the talk. So any questions for Rob?
So in this proof, you're choosing some intervals and then pushing on those intervals. So can you actually find these intervals and find this pushing? Like, is it constructive up to the discrepancy theory part?
So yeah, great question. So one of the motivations of this Loveit and Mecca proof was that their proof is algorithmic. So the way I stated it's not, but right, you can turn this into an algorithm for finding these this pushing. So I have no idea how efficient this algorithm is, but yeah, this can all be made algorithmic. So one should be able to find these things. Like I said, I'm not a programming person, but hopefully someone will use this to find these things on whatever degree 10,000 or 100,000 or whatever you can do, 10 million. I have no idea. But right, yeah. So the cosine polynomial is totally explicit, and the sine polynomial. So you can make this into an algorithm. I think a polynomial time algorithm.
Other questions? So I missed a little bit about this this push thing and how it's related to the toy problem. So when you push, you have this definition of the two sets. Was it called SC or SC?
Yeah, right. So yeah, C's already given. So you got your S are the ones you got left to pick.
So you pick the coefficients in the S, right? But you are not pick it just like randomly for each one. You pick a direction. You have to do it in stages, like because
Right.
your problem you have to do in steps and push it.
Yeah. So yeah. Yeah. So I was lying a bit in the toy problem. The toy problem looks like it's online. Looks like you're picking them one at a time. But actually, we're not doing that. We're choosing them using this Loveit and Mecca theorem, or using Spencer's theorem, if you like, or using Becks method, which are all sort of different versions of the same thing. So right. So how are we choosing the epsilons? We're choosing them in an offline way. We see all of the sets.
Mm-hmm.
We know all of the sets we're going to see throughout the process of the balls, and then we're releasing a Brownian motion. And then when that hits a hyperplane, then we're fixing it to that hyperplane and working inside that hyperplane. And then we're sort of, if you like, running this Loveit Mecca algorithm to find the epsilon k's. But yeah, we're not doing our heuristic. The heuristic was just to sort of to feel why it should be true, just to push us in the right direction. So, but if you do the argument that I said for the heuristic, you would get the result with a log n squared error or something.
I see. So if you, for instance, if you just randomly pick the sign in S, right? What discrepancy would you get?
So if you pick them really randomly,
yeah,
then you get something terrible, because you just end up with a random polynomial. Yeah, then it will be totally hopeless.
I see.
Yeah, but
even the
yeah, you need this drift, right? So if you choose them according to the votes, if you pick the directions randomly,
you really have to pick it so that it reaches the standard deviation part.
Like, yeah, exactly. The drift has to beat the standard deviation. Exactly.
I see.
Yeah.
Okay, so it is a deterministic algorithm for the sine function, or is it?
No, it's a randomized.
So some Brownian motion, and you like to walk, and then
yeah, exactly. So yeah, so they run a Brownian motion, but some sort of dependent Brownian motion. Yeah, it's a lovely paper, this one of Loveit and Mecca. It's really very
interesting. Yeah, and also another question, maybe quite silly though. So the pushing thing that is trying to fix the problem with the cosine function, which gets close to 0, right? Does that affect at all to those good intervals at all?
No, so they're completely independent, because they're working in different dimensions.
I see. So it only fixes the imaginary.
Yes, the cosine polynomial determines the x coordinate, the real part of the number, and the sine polynomial determines the imaginary part. Yes, that's the nice thing. You can separate them completely. Yeah.
Okay. Okay. Thank you very much.
Sure.
Other questions? Okay, if not, let's thank Rob again for the nice talk. and then now we have the grad house time.